Hello and welcome to Wednesday's edition of Cracking the Cryptic, and today we're going to be taking a look at a very colourful puzzle called Regional Differences by the constructor Lake. And the reason I'm doing this is actually because of last night's stream, where, well, we had a wonderful time. Thank you very much if you joined us. Mark and I were solving Sudokus from our 600,000 subscriber celebration pack. And we got through four Sudokus, and then we did a crossword at the end. The crossword was actually quite good. It had a theme, which chat spotted, but we didn't. And it was most entertaining. But one of the people watching was the constructor, ThePedallingPianist, who wrote to us overnight, really pushing this puzzle. I had a quick look on Logic Masters Germany. It's very highly rated, with some super comments from some very well-known names in the Sudoku community. So I thought I would give it a go. I hope that's all right. Thank you to the Pedaling Pianist for the recommendation. I'll say more once I've finished the puzzle and we know how good this puzzle is. But yeah, I'll read you the rules and tell you what these lines are new. This is all these lines, I think, have the same property, and they're just different coloured for sort of artistic merit. But I've not seen lines with this property before, so it is going to be something where we're going to have to learn together. Now, what else happened? Well, we had our stream. I told you about that. Over on Patreon yesterday, we released our brand new Sudoku hunt. We've already had loads of you who have managed to solve all the puzzles. It's quite ridiculous how clever some people are out there. But if you've not had a look yet, it is a really wonderful Sudoku hunt themed on Halloween. Caroline's Halloween Adventure from the Paint by Numbers Institute, featuring lots of Japanese Sudoku puzzles. And they're really lovely things, actually, because you always get a picture in the grid. So you sort of get a bit of, confirmation you're on the right lines, especially if you're good at nonograms or those sorts of puzzles. So check it out. It is meant to be approachable. It does seem to be more approachable than last month's. And yeah, basically, you'll get a lot of fun out of it. Now, what else? I've got some birthdays to do. Why don't we do those? Josh, over there in Tennessee. It's your birthday, your 27th birthday today, and I know this because your partner Annie wrote to us and told me that I also had to say happy birthday from Finn, June, and Lucky. Is that Lucky? I can't read my own writing. They might be your cats, I think. I'm not sure, but anyway, Josh, I hope you have an absolutely brilliant day today with a large helping of chocolate cake, of course. Now, to someone else who watches a lot, Michael. Michael, it's your birthday today, and I know this because your partner Sabrina wrote to us and said you might like a shout out. So I hope you do, and many happy returns. I hope you also get chocolate cake. And then I'm late with the next birthday, but it sort of wasn't my fault. We only got the request yesterday, which was actually Caden's birthday. Caden turned 6 yesterday over there in Beckley, West Virginia. Caden, I'm always so thrilled when I hear about children, especially young children, watching the channel. And I understand you started watching during COVID, so when you were even younger. It's absolutely brilliant. Thank you very much for watching. I hope you had a brilliant birthday yesterday. I'm sure you had cake. I don't know whether it was chocolate, but I hope it was. And with that said and done, let us turn our attention to Regional Differences by Lake, and I'll read you the rules of the puzzle. They are normal Sudoku rules apply, so we're going to have to put the digits 1 to 9 once each in every row, every column, and every 3x3 box. Now let's read this carefully. Box borders divide lines into segments. Each sum of adjacent segments on one of these lines has the same difference. So let's look at this blue line. In fact, that's all the rules. I was preparing myself to read the next rule, but the next paragraph says the different colours do not mean anything. They just make the puzzle look more colourful. So what we have to do is divide the line into segments, or the box borders divide the lines into segments. So actually yellow's a terrible colour. Let's go for purple. Then that one can be grey. Oh, there's loads of segments for this line. I probably shouldn't have chosen this line. Let's make that blue. Okay, so the line actually is divided into 5 segments. So, and the sum of adjacent segments. So what we'd have to do is we're going to have to add those digits together and compare it with the purple total. And these are going to have a difference. And then the difference between the purple total and the grey total will be the same difference. And then the difference between the grey total and the orange total will be the same difference, etc. So it's a very interesting rule set. And do have a go. It's got 4 stars out of 5 for difficulty, so it's clearly not a walk in the park. But hopefully we're going to take a stroll in Logic Land and get to the oasis that is the solution by the end of the puzzle. So the way to play, click the link under the video as usual. But now I get to play. Let's get cracking. Now, do we start with this great big line here? Or do we start with that line, actually? That line might be better. I'm very unsure. Or maybe even that line. I'm not. No. Okay, you don't start with this line, do you? Because that could just be 1, 2, 3. Because if this... Let me just show you. If that was 1, 2... Whoa, 1, 2, 3 like that, then the difference between 1 and 2 is 1. The difference between 2 and 3 is 1. So we have the same difference along the line. But then you could just reverse this into the other direction, and that would work. But you could also put, you could do 9, 8, 7, etc. And then you could have different differences. So that line, okay, the pink line, pink/purple line is not where we start the puzzle. This line is probably going to suffer from the same fate then, isn't it? The only reason I was interested in this line is I was wondering whether we could do sort of region sum line logic on it, in the sense that there is quite a big difference in length of segment between the box 2 component and the box 1 components. And I guess the box 1 components have to be different as well. What I mean by that is that the minimum these digits could be would be 1, 2, and 3. Now 1, 2, and 3 add up to 6. So no, I don't actually think that's going to... I think we are going to suffer the same fate. Because you could do something like... Well, then we're going to have to define the difference. What you can't do, actually, I hadn't looked at this given 9 until now, but you can't do 3, 6, 9, because the 9 that we're given will stop that. But you could do 4, 6, 8. You could do 5, 6, 7. And you could not have 6 here. If you had 7 there, you have to be a bit careful then, because you couldn't have a difference of 2, could you? Because that would create 5, 7, 9. But you could have a difference of 1. This could be a 6, 8 pair with a 7 here. No, okay, sorry. Right, I'm probably am meant to start with a great big line here, where so the difference between well, I'm going to have to talk about the secret. There surely will be an occasion. I don't know if it's right now, but the fact that this line overlays the entirety of box 1 makes me think the secret is going to be relevant. So let's talk about the secret. The secret of Sudoku. It's something I share with only my very favourite people, and apparently we nearly have a t-shirt coming out that says this. I apologise for that, but some people have asked for it. The secret of Sudoku is that this entire box, because it will contain the digits 1 to 9 once each, sums to 45. And the line in this box, look, only overlaps 8 of the cells. So this cell is defining the difference between this segment and this segment. So imagine that was a 5. So this is going to sum to 45. This is going to sum to 40. Right, and then this, right, I see. So then the line in box 7 can't, what we can't do is go back up to 45 again, can we? Because this only comprises some of the digits in box 7. In order to get back to 45, it would have to comprise the entirety of the digits. So what that means is that if we went 45 to 40, this one is going to be 45, sorry, yeah, to 40. This is going to be 35. And these two digits are going to sum to double this digit. Then what happens? So we'd then be on 35. It feels hard for me, I mean, using the 5 example isn't proving that this isn't possible, but it feels hard to believe this is going to go back up again, doesn't it? If that's, which way around is it? If that's, oh, it can't be 9. If that's 8, this would add up to 16. No, it can't go up again. So what I'm looking at is this line segment here, and I'm trying to compare its value to this line segment. That is what I'm trying to do. And what I'm thinking is that there are 4 cells here in box 8 that are not on this line segment, and the minimum they could be would be 1, 2, 3, and 4, which sum to 10. But yeah, that's the easiest way to see it, isn't it? So that's the minimum sum of those 4 digits. Now, if we were going, if the order of progression along the segments was 45, lower than 45 by this, lower than 45 by double this, if we were going to go back up again, then the difference between the original 45 and this blue segment is the same as this, isn't it? But this is a single digit, and there are 4 digits there, which cannot, the sum of these 4 cells cannot be a single digit because they will add up to at least 10. So we have learnt something, and that is that we go 45 lower by this, lower again by 2 this, lower again by 3 this. Yeah, so if this was 5, this would add up to 15. And then and then what do we do? Do we go back up, or do we stay low? Why is that not obvious to me? So at the moment we're on 3 times this segment is 3 lots of this less than this. So in my example, 40, 35, this is 30. I mean, my example doesn't work for going lower again, because this would this would only add up to 25, and it's a 7-cell segment, and that's too low for a 7-cell segment. Even if we put the lowest digits we could on it, would add up to at least 28, wouldn't it? So that won't work. Which is perhaps interesting, or perhaps not interesting. Yeah, and then we're going to have to work out what it does after that. Okay, let me think about this again. So if this was 8 and this was 16, we then worked out that this is 24, haven't we? So we certainly can't be taking this. Hang on, hang on, I'm going to do this again. This is 24, so by the secret this is 21. And if we go down again, that's far too low. So we have to make this low in order that this could work. So let's make that. That's got to be 2, hasn't it? At least, because these two squares have to be capable of summing to double this value. So if this was 1, these would have to sum to 2. That doesn't work. So if this was 2, these add up to 4. No, that doesn't work because these would then add up to 8. And there's 4 different numbers. So the minimum number here is 3. So if we go 3, 6, hang on, no, that's 9. That still doesn't work. Am I being dense here? I feel like I am now. Sorry. If this is 3, this is 6. These 3 we're still going lower by 1 difference, so that's 9. That doesn't work. 4. If this is 4, this is 8. Oh, that works, because then I get 12, and I can make 4 different numbers add up to 12. And in that situation, well, in that situation, what's the value here? 12. These are 33, aren't they? Yeah, so that could work. Because if we then go down again, these would add up to 29. And that feels like it's possible. Although, no, it's not possible. Because then... No, that's okay, isn't it? I think it's okay. 29, these would be these would have to add up to 16. They would be a 7-9 pair. So okay, so this can go down. Maybe it has to go down because if it sorry, I'm not doing a very good job of articulating exactly how this is meant to move. There's something weird about this. There really is. If it goes back up again, then the value of this is the same as the value of this, which means the value of this would be the same as the value of that. But providing these don't have a single digit total, I think the world would make sense in that regard. Okay, so how do we decide what this is then? So this is now 4, 5, 6, 7, or 8, I think. So perhaps we have to think about this line, do we, to try and understand whether or not there's some different principle at work. I don't know. How does this line split up? So we get a 2-cell segment, then a 3-cell segment, then a 1-cell segment, but then a 2-cell segment again. Now, what is the problem there? I suspect there isn't much problem. If this is 4, this is 8, these are 12, but the yellow line's contribution is not 12 because we have to take into account this digit. So 8, imagine that was a 2, say. These would be 10. Yeah, that could be 8 again, and then that could be 6. So I think, is that a difference of 2 I had along the line? I think it was. That seemed to work very nicely. Okay, so I don't understand. I don't understand how there's any restriction on this. Yet, I feel... Actually, I might have a look at that green line in a minute, because that green line is comparing single-digit totals with a 4-digit total there. So maybe it's there that we need to look. Although... If you were designing this puzzle, it does feel like you would start off with the massive line rather than the green line. And my spider sense tells me, or is making me think there's something about the interaction of green here with blue. I just can't work out what it is. Maybe I'll try a different number there. If that was 6, this would be 12. These would be 33. So this would, we've worked out that's lower, haven't we? So this would be 27. And then this would be 20. Oh, 21 is far too small. It's far too small. Yeah, so I do have to be a bit careful. In most situations, this red line in box 9 is going to be the same total as this green situation. And the only situation where that doesn't work, was it when this was 4 or 5? I can't remember. So if this, let's go back to if this was 5. If this is 5, this is 10. This is 15. So this is 30. That can't be 25. So if that's 4, 8, 12. Yeah, this is the one where it works, isn't it? Because that's 33. And this could be 29, I think. So we don't have to go back up again to 37, which is the sum of light green. But that's the only way that works. So how would that look from the yellow line's perspective? Because, so what we're looking at is this being 4, this being summing to 8. That's what that that's what that means. This summing to 12. That's not the yellow line though. Remember, this digit is not on the yellow line. But that 8 is true. This would sum to 12. This would sum to 16, wouldn't it, I think? Because the difference between this one and this one requires this to be 16. Oh, that, well, that doesn't... How are we going to do that? So, the power, sort of... that's impossible, I think. I don't think that works. How can I do that? I've got to get from 8 to 16 in 2 steps effectively. So I can make this yellow line to add up to any number that is below 12 by putting a digit in here. So I could make it add up to, well, it's going to have to be even 10. No, it just doesn't work. The gaps are wrong. We essentially need to say that 8 plus 3x is equal to 16, and 8 is not divisible by 3, so it doesn't work. Ah, that's interesting. Okay. So now what we've worked out, that is right. 8, gap of something, gap of something, gap of something. But when I know that's 8 and I know that that's 16, it can't do it. You can't do it. I am convinced. I've thought of a way I could actually, hang on. What about if I went 8? No, I can't make that add up to 16. I was wondering about going 8, 16. 8, 16. Oh, I didn't think of that. Sorry. I'm going to have to go back. I didn't think of doing... No. Because this can't add up to 16 if all 4 digits only add up to 12. So that is not possible. But is there some high lower t? No, there isn't. There isn't. I just had to convince myself that there wasn't a way of doing that. Okay, so what that means is that this segment I'm going to make light green again. This is the same total as that, and that is the same total as that. But now, hang on, now I've got another problem. I've broken it in a different way. Because if purple has the same total as purple, and yet I've got to have a difference between purple and that. And then a difference between this and that. I can't get back to the same... I can't. So let's say I increase from purple here to here, which is very likely to be what I must do. But let's just say we increase. Then for this one, I have the choice. I either increase again, or I reduce back to the value of purple. But there's no way then I can... If I've increased by 2 steps, and I'll only be able to reduce it by 1 step, and I need to reduce it by 2 steps to get back to... I know. Right. Okay. But how about... Let me go back to the rules. Okay. What if the... Right. So I'm not being terribly articulate. I'm finding this quite hard to think through. But what if the difference along the yellow line here, no, the orangey line, this line, was 0 from box to box? Then I don't have to worry about higher t and, increasing steps or decreasing steps. Is the only way it could work, I think. So I just want to explain this again. What we've concluded so far is that whatever the value of this is, we don't know. Whatever the value of this is, the steps that the red line is performing is down, 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 up. In other words, these cells and these cells have the same value. So purple and purple have the same value. But when we then try and fit that into the paradigm of the orange line, if there is any difference as we go from segment to segment along the orange line, it cannot work. Because the difference, let's say there's some difference that's not 0. It doesn't matter if it's positive or negative. Then the difference between purple and this segment is x. And then we have a choice for this cell. It's either going to be back at purple again, or it's going to be 2x is the difference between purple and this cell. Now, if it's back at purple, then there must be a difference between purple and this purple. That's not possible. And if it's 2x, I can only reduce it by 1 lot of x to get back towards purple, but I can't get it back to purple itself. So you can't do it. But now what we've worked out is that the difference between these two cells, well, this is big. It's going to rule 8 out. Because what we're saying is that the total of that segment is the same as the total of that segment. So if this was 8, we know this is 16 because it's 2 lots. That's 16, but both would be 7 9s, and I get too many 7s and 9s in row 8, so we can take 8 out. If it's 7... Oh, GeForce Game Driver is available. No, I don't want it at the moment. So this would be 14. That's 7. That's 14. That's... Oh, well, you can't... Hang on, you can't... hang on. Everything breaks apart from... Everything... That's it. Everything breaks apart from 4 because we tip into this box. Oh, that's beautiful. What a beginning. Right, this has to be 4. And the reason it has to be 4 is the difference along this line is is 0 in each case, but we know that this is twice the value of this. Now, if this is anything else other than 4, then this will be 10, this will be 10, if it's 5, say. This is going to be a double-digit number for all other numbers, because it's 2 lots of this. So that's got to be 4. That's got to be 8. I feel like I must know that number now. Yeah, that must be right. Is that 4 or is it 8? Because this... The difference between this and this was what? It was one lot of this, wasn't it? Yeah, so this is going to be worth 8, this is going to be worth 8, but we need another difference of 4 in here to make sure that this is 12 different from green. This is quite confusing. I hope you'll forgive me. But, oh, well, this is good, because this adds up to 8, and it doesn't involve 4, so that's 1, 2, 5. What? This is bizarre. It's brilliant, but it's bizarre. Now... what does that mean? We can actually, can we propagate this up here? I've not really thought about that box. We probably can. Because what are we saying now? The value of green is 37. These squares are either 1, 7, 2, 6 or 3, 5. That's an appalling pencil mark, Simon. Oh, but it does, I tell you what it does do. It shows me that 4 is in one of those 2 squares in box 7. So 4 is in one of those squares. 4 can't go there because remember this adds up to 8. So it would be double 4. The flavour of 8 that this is different from the flavour of 8 that this is. Oh, what would be good? I tell you what would be good. It's not true that that's a 1-3 pair, is it, to add up to 4? It might be. Oh, I wonder. So we know this adds up to 37. Well, okay, yeah. If we go up from 37 by 4, which is the common difference along the red line, those squares add up to 41, which means these 3 squares need to add up to 4 to make the box add up to 45. Well, that's not possible if this is an 8. So what we must instead be doing is going down from 37 to 33. So this segment adds up to 33, which means these 3 squares add up to 12 to take us back to the secret. This is a 1-3 pair, and therefore this is a 2-6 pair because it has to add up to 8, and it doesn't involve 1, 7 or 3, 5. 2 and 6 come out of this option, which is now 1, 7 or 3, 5 only. And now... well, now I'm feeling a little bit better than I was without being breathtakingly confident that I've advanced the cause much further. Can I do some Sudoku here? I mean, it would be outrageous if Lake's making me do Sudoku at this early juncture. I don't know. Is it the green line now? Oh, I tell you what it might be. Is it that line? That can't have a 4 on it now. Wasn't that one of the options we looked at? I remember thinking about this adding up to 7. Well, yeah. Oh, sorry. I just flicked. I'm not used to having a hoodie, and the toggle thing hit the microphone. Right, I'm going to look at this. What's the total of those digits? And the answer is I don't know. But, well, actually, maybe I do know. I might know now. It was never 9, was it? Because it is clear that these two digits are different. So there is, we're not falling into the trap we fell into on the orange line. There is a difference of something along the yellow line. So this is the middle value. So if this was 9, one of these would be higher than 9, and that's not possible because they're both single digits. If this was 8, one of these would be higher than 8, and that's not possible because we've got a 9 in the box. So the maximum sum of these was 7. But there's a 4 here now, so 1, 2, 4 doesn't work. So this actually does add up to 6. So that's a 5. Here we go. This is now a 6 by Sudoku. That's a 2. The 5 takes 3, 5 out of here, so this has become 1, 7. There's a 1 down here by Sudoku. There's a 2 down here by Sudoku. There's a 7 in here by Sudoku. Here we go. Here we go. That can't be 1 by Sudoku. There are lots and lots of low digits in column 4, so the remainder of these squares are 6, 7, 8, 9. That's not 8. That's on the... Yeah, same logic I applied here applies here. This can't be 9, can it? Because one of these would have to be higher than 9. Because they can't be the same digit. So this adds up to 6. So then we have to... okay, so the difference on this line is either 1 or 2. Now if it's 1, these are a 5, 7 pair. And if it's 2, these are a 4, 8 pair. Sorry, not that one. These two. And that doesn't help us. Bobbins. Right. Okay, I think I am going to finally have to turn my attention to the green line. How does this work then? The minimum sum of those squares is... well, it's actually higher than... I was going to say 10, but it's not 10. It's 12, because these two squares have a minimum value of 9 if they were a 4, 5 pair, because they can't be 1, 2, 3 or 6. So 9 plus a 1 plus a 2 is 12. So again, right, the first thing we can establish is this is not a difference of 0 line. I'm going to try and make sure that I consider that much earlier for all the rest of the lines. So there is a difference because this is a single digit total and it goes up to at least 12. So from here to here we ascend, don't we? We ascend by at least 3. Because even if this was 9, that's at least 12. So does that mean... I want to say this has to be low then. Yeah, because this is a single digit total. So if this was a high number, we know the difference is at least 3, don't we? So let's try and put 9 in here, for example. That would take us... Well, the point there is this would have to be lower than 9, because it can't be higher, and the difference is 3. So then we'd have to bounce up again, but we wouldn't get to a 12 here. So this is low, and we're stepping up to this value. And the minimum size of that is 4. So that if that was 4 and we stepped up by 3, we'd get to 7. That doesn't work. Because we have to get to 12. So we cut. This might have to be 9, actually. That might be what we're intended to deduce from this. If that was... Yeah, alright, let's think about this a different way. How could that be 7? We know the difference to this digit is at least 3. Well, therefore, we'd have to go down, and then we'd get back to 7 for a total that must be at least 12. That cannot be 7. If it's 6, then this could be 9. And that could be 12. That's probably what it has to be. It probably has to be 6, 9. Oh, no, I'm wrong. I'm immediately wrong. Because, okay, yeah, this could be very low. Because, yeah, providing this is 9, then the difference between 4, 5, or 6 or 9 is plenty. In fact, it's increasing. If that was 4 and that was 9, then we'd go up to 14 here, which is fine. We're taking all the pressure off. But I don't think this can be 7. Because the only way it can be 7, the difference we know between 7 and this digit, well, the reason it can't be 7 is that we know that this is a single digit total, that's 12, so we know the difference is at least 3. So if this is 7, this has to be 4, but then the difference is 3 and we don't get to 12 here. So this is not 7, this is 9, but we don't know what this is. And if it's 6, this is 12, and this is a 1-2 pair. Oh, that would be a 4-5 pair, that works, okay. Okay, but what's the value of those then? So we're going, well, we don't know. We don't know actually. Because, no, we really don't know. The reason we really don't know is that if this is 6, this is 12, and the difference is 3 along the line. So this is either 9, which it could be in one way if it's 4, 5, or we go up and it's 15, and that would be 7, 8. But that's if this is 6. If this is 5, then I think the pressure comes off here and changes its nature here. In fact, maybe 5 to 9 is 4, a difference of 4, so this would be 13. And this would be... okay, but if this is 5, you have to... no, that doesn't work. Oh, that's rather pretty, actually. Let me show you that. If that's 5, because the difference is 4 on the line, and we're going up to this value, this becomes 14. Now, there's no way we go back down to 9 here. Because this is 5, there's no option to make 9 in this domino, because 1, 8, 2, 7, and 3, 6 have been ruled out by this, and this being a 5 rules out 4, 5. So we have to go up again. And we have to go up from 13 by 4 to 17, and that's ruled out because of this 9 in the corner. So that is not 5. Now if we go 4, are we going to have to go up again? I'm not sure. If we go 4 to 9, difference of 5, this is 14. So we can't go down to 9 again because the 4 also rules out the 4, 5 pair from here. So we have to go up. And I'm going to break the bank, aren't I? I think I am. Yeah, I've got to go up to 19 or something. Because the gap is 5. So this is 6 always. The gap is 3. This is 12. So this is a 1, 2 pair. This is a 4, 5 pair because it can't be 3, 6 because of the column. And, but then we don't know what this is. Because that's the way we started. This was either 4, 5 or 7, 8. Ah, okay. Sorry, now staring at this, wondering what that means. It does mean I can do some Sudoku. I mean, it's outrageous again, but look, 9 is in one of those squares, and therefore 9 is there. Therefore 9 is in here. 9 is in there. That's a very likely place for it, isn't it, I think? Oh, this is gorgeous. Right, look at column 8. What digits do we have left to place? Well, 7s and 8s. So how could this be a 7, 8 pair? It can't. It would break that square. So this is actually a 4, 5 pair, which means that is a 7 or an 8. So that's the higher, that's the higher of the two digits, which means this is a 4 or a 5. That means I've got a 4-5 pair in row 3. That digit, which is a 7 or an 8, where does it go in this box? And the answer is I don't know, but it's in the squares that the 9 lives in. It's one of those, so that's a 7, 8, 9 triple. These squares are 3 and 6. Chance for a 3 in the corner. That's not 3. This is a 1 or a 2 by Sudoku. Oh, look. This is a 7, 8, 9 triple by Sudoku. And can we do anything with that? Possibly, but I don't know what. There's an 8 there, so that's a 7. Let's deal with that. That's an 8. That's a 7. That's probably going to give us this line, actually. So let's just deal with some quick bit of Sudoku and go and look at this. So this is 6, that's 7, so that's 5, because the gap on the line is 1. So that's 5, that's 4. Here we go. Here we go. No, we don't. Here we went. there we went, and there we failed. Oh, bobbins. No, actually, okay. No, that has just totally... Oh, that's a 1-2 pair, is it? Yes, okay. So 1 in the bottom row might be fixed. I get a 1 in the corner, apparently. So 2 is in one of those squares. 7 is looking at that square, so that is useful as well. So that gets me a 7 here. So there is definitely Sudoku to be done, isn't there? 3, 4, 5, 8 into this box. Can we do anything with that? 3, 5, 8 into those squares. I mean, I'll pencil mark it, but I can't see how to resolve it. Those two squares are the same, because this digit has to go into this box. So that is an odd digit. Yeah, that's an even digit. Look, these have different parity. So this, again, this line is not a 0 difference line. In fact, how many lines? I've only got 2 lines to look at, actually. I've got this line, the blue line, and this line. But maybe this is the line we need to think about, because one of these must be higher than this digit. Ah, 7 here. How did I get that? No, that 7 is valid. I was thinking, how did I get it? But no, that makes sense. So, oh yeah, 7 here. Here we are again. How many 7s have we got? We've got a few. It'd be useful to know what this is, wouldn't it? That would help us. In fact, look, if that was 7, the difference on the line would definitely be 1. But if this is 9, then the difference could be 3. The difference is odd on the line, obviously, because we're comparing an odd number and an even number. Maybe it's this digit then that we have to think through. Let's look at the options. It is, from a pure Sudoku perspective, 2, 4, 5 or 6. But, yeah, but by parity, yeah, the difference along the line is definitely odd. So the total here is even. Oh, that's so good. Yeah, I mean, look how beautiful that is. Literally, knowing these are of different parity is telling us that digit. Because the difference between this is an odd number. So the difference between this odd number and this segment is an odd number, which means this is adding up to an even number. And the difference between this even number and this needs to be odd. So this is odd of its nature. And 2, 4 and 6 are all even. So that is 5. That's just forced. So this isn't 5. These squares are now fixed. Look, they're 2, 4, and 6 just by our old friend Sudoku. That is. That's 3 in the corner. That's 3 in the spotlight, losing its religion. This is, well, where's 5 in column 9? That's 5. That should be 8. I haven't put an 8 into this column, so that's 4. That's 3. This is not 9 anymore. 3 and 9 are a pair in box 8. Look into those squares. Oh, I see. And this bottom line is 6, 7, 8, with that not being able to be 6. Let's get rid of the 7 corner mark. There's a 6, 7, 8 triple in column 4, which seems to mean that's a 9. So there's a 9. There's a little X-wing of 9s in boxes 4 and 7, which may or may not be relevant. I need to think back on the blue line, but let me just see if we can do. Yeah, we can do more Sudoku. Where's 6 in row 8? It's there. So these squares are now 2, 4, 5. Look, to complete row 9, and we don't know actually enough, but we know a little bit. And these squares are 3, 8, 9, and that's not 9. Well, no. No. Okay, that is valid. That cannot be 3. Because if it's 3, the only component of this that will work is 6 with a difference of 3, and that's going to make that 9. It's going to go 3, 6, 9. Can't go 3, 7, 10 for obvious reasons. So this is 8 or 9. This is the big digit. So well, the problem is that takes all the pressure off though, doesn't it? Because this could be 6, 7, 8. That would be legitimate. It could be 5, 7, 9. No, it can't be that actually. What about 4? 4, 6, 8. Oh no, that doesn't work. Okay, what about 3, 6, 9 then? I think that works. 3, 6, 9. So there's hang on, is there always a 6 on here? I don't think that's going to do very much. It would eliminate 6 from those two squares. Let me just think that through. 6, 7, 8 is one option, and that's a 6. 3, 6, 9 is the up. So there is always a 6 in that domino. So these two squares can't include 6 anymore. Because if there was a 6 here, this would be a 3, 7 pair, and 3 and 7 are 4 apart, and this would break. 6 is not there. So 6 is in one of those squares. It might be Sudoku actually that we need to think about. What about, is it something to do with 7, 8, 8 in this? No. Oh, well, probably not. 1, 2, 3, and 8 into these squares. Can we put 8 on this line here? That feels awkward. Because no, you can't put. Well, you probably can actually. Sorry, I was thinking. I was thinking this can't be an 8, and it couldn't be if it was the only number. If this blue segment it didn't work, and this was an 8, the difference here would be even, and we know the difference along the line is odd, so that couldn't work. So, and we know the maximum difference is 3, isn't it, with a 6 and a 9. So if this is 8, how do I do? Oh, I'd have to go 8, 1 is how you'd have to do it. Which might work actually. So 8, 1 is 9. This would be 6. That would be 9. Oh no, that's got the wrong difference here now. I think there might be a problem with 8 in column 3, but actually in my mind's just I want to have another think about the difference, because once I've worked out this is 5, what I never did was to consider what this is, and that was probably remiss of me. I mean, if that's 7, this has to add up to 6, and if that's 9, this has to be a 7, so this adds up to 6 or 7. Which seems to have some relationship to that, but it doesn't really, does it? So this adds up to 6 or 7. And the difference on the line is 1 or 2. But we know the difference is odd from this relationship, so the difference is 1. Ah, that's interesting. Yeah, that is interesting. That means I definitely can't put 8 here. This line has a difference of 1 on it. In fact, what that means is, because we worked it's a difference of 1, and this is a 5, this adds up to 6. That is right. That is definitely right. But, okay, it's either 1, 5 or 2, 4. Now we can get rid of 5 from here and 1 from here, therefore, by Sudoku. We've got a 1, 2, 4, 5 quadruple in the column. So 3, 7, 8 and 9. This digit is only 3 or 7. It can't be 8 and it can't be 9. Okay, but this is 6, so this is 7. That's annoying. That can still be 6 or 8. Okay, but no, it's difficult because we're still dealing with dominoes here. All right, I'm going to go back to my earlier thought. Where's 8 in column 3? It can't be there. It can't be there because we've got an 8 in these two squares. Now, so the only question is, can it be here? But if it's here, then this obviously becomes a 6, doesn't it? If you put 8 there, that immediately becomes a 6. And that implies that the difference on this line cannot be 1, which it needs to be. So I think the 8 can't go there, and I think the 8 has to go here. So that's 3, that's 9. Which means that isn't 3. Oh, nearly asked the question where's 5 in column 1, but it didn't work. 9 is here, using our X-swing that we had. So how many 9s have we got? Loads, but not... No, we've got another X-swing, haven't we? Oh, this is an 8-9 pair. There we go, there's some more Sudoku to be done. 7, 9 over there. 2, 3, 8. Maybe we could do... I don't know, one of those is a 6. That's not useful, I don't think. What's going on in column 1? 1, 2, 5, 8. So that square is interesting. That's a 1 or a 2. That is very interesting. That gives me a 1, 2 pair. That seems to make that an 8. That a 3. This a 3. Aha! So these squares are 4 and 6. Which I can't do enough with. What about that? 1, 2 or 5? I still haven't worked out what this domino adds up to. We might be closing in on that though. 2, 3, 4, 6 into this square. 2, 3, 4, 6. If I get the parity of it, that would be useful, wouldn't it? Because we know the parity of this overall is definitely odd, because that is even. But I'm not seeing how to do that, I have to confess. What about... In fact, it's a bit worrying now because I think I've only got this blue line to work with. That does seem to be the case, so I need to understand something more about it. Oh, okay. No, what about this line? Surely this line is relevant. How could that be 3 now? That won't work. That's a 6. So if this line's going 6, 7, 8, I mean, there is, yeah, it just is, isn't it? That's 6, that's 7, that's 8. So that's 3. So that's 3 and that's 1. Okay, so surely that does something. Gets rid of 4 from here. That could never have been a 6. This row needs 2, 5, and 6. So that is a 2 or a 5. 2, 5, or 6 here. That's not 6 anymore. That's not 4 actually, because of this 4. So that's 2 or 3. There are 4 3s looking at this box. That's 3. And that is huge because this is now even and has to not be 4 or 6. So this is 2 or 8, and 8 will be too big. That's beautiful. So because we know this sums to an odd number, and that's odd, this needs to be even by parity. Now if this is 8, it can't be 4 or 6. So if this is 8, this is 11. But the difference along this line, remember, is 1. So that's too big. So that needs to be 2, 3 adding up to 5, which means that's 6. That's 7. And then we worked out, didn't we, that this, yeah, because this is 5, this is adding up to 6. Oh, we still don't know. Well, I know that's not 2. So I know that this is a 1 or a 2. You're kidding. How is this not resolved? Okay, well, let's try. Well, that's a 2, so that's a 5. So maybe that does it. This is not 5. This is a 1. Yeah, no, that still doesn't do it. Really? What's this then? 8. Oh, I see. That's 6. That's 4. That's 1. That's 2. That's 2. That's 1. That's 1. That's 2. This is 6. Ah, that's done it. So this is 4 by Sudoku. So this goes in. That becomes 5. That means this is 1. 5, 4. 1, 2. 2 by Sudoku. 4, 8, 8, 9. 9, 3. 5, 2, 4. 8, 7, 6. That is a spectacularly clever puzzle. It's taken me over an hour. Well, actually, I think I was very slow to understand how the big red line works. Is it right? It is right. Oh, goodness. That's a very old puzzle. Sort of 6 months old, isn't it? Wow. Well, I didn't know that. I thought it was newer. But the Pedaling Pianist has done us all a fine service by recommending Lake's puzzle. That's really clever. It's really clever. My favourite bit was that this orange line. I thought it was broken. I couldn't see how it could work. And then you have the epiphany, oh, it might be no difference along it. And then it sort of does work, but it's still sort of, it's still really interesting how it unwound. I really like the fact I could get that digit as a 4, and that told me the nature of the 8 line. I was about to call it the 8 cage. It's a beautiful puzzle. It's got really clever ideas all the way through it. And the other digit I really liked. Well, I liked the fact I could do parity on this stuff, on this blue line. That seemed to be parity was quite relevant. Actually, this was pretty. The green line was pretty as well, wasn't it? With the way that this got narrowed down. It's just quality, it really is. That's a very high-class puzzle indeed. Let me know in the comments how you got on. I enjoy the comments, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.